So in this video we are going to talk about the Lagrangian and the introduced Lagrangian mechanics. So how was it born? During Lagrange's time it was already known that light, when it has to choose a path between a point A and a point B, it will minimize its time. So if, for example, A and B are in the same medium, so for example in vacuum, it will go in a straight line because it's the way that will minimize time. And if there is a change in medium, so for example it goes from a fast one to a slower one, so for example vacuum, water or something similar, it won't go in the straight line anymore, but it will actually do the path that minimizes time. That will be so two different straight lines. It's like when, if you're with your car, you have to go from home to your office, and you know that a part of the street has some high quality streets and another one is only mud. You will of course not choose the street where you have to do more mud, but you will try to optimize it in order to do as little mud as possible by optimizing time. So normal objects in everyday life don't act as light, so they don't minimize time when they choose their path. Of course, when I say chooses, it doesn't mean that the object really has a consciousness or knows future. This is simply a mathematical approach, a model, where we consider the whole path, the path as a whole. In Newtonian mechanics, the thing is that you discover your path moment by moment by considering forces. So it's a completely different approach, but of course, particles keep not knowing the future. So the question is, what does a normal object minimize when it has to choose its path? Lagrange decided that it has to minimize something that he called action. So he created the principle of least action. So the differential of action must be zero. Like in every function, a minimum must have its differential that must be zero. Now, what is this action? He defined it as an integral between the starting time and the end time of a scalar function he called Lagrangian. And as I said, it's a scalar function, so this makes things quite easier than when with Newtonian mechanics we have to work with vectorial functions. These functions, the function depends on positions, velocities, and time. Now, there are some things to say about it. First of all, why does it depend on positions and velocities, and not only on positions, for example? Now, I'm not going to demonstrate it, but you can intuitively understand that to know everything about a system and in the same time to know how it will evolve in the next infinitesimal increase of time, you have to know both the position and the velocities. For example, if you ever had done some kind of molecular dynamics, for example with GROMACS, you will see that in GROMACS the .gro files actually contain both the coordinates and the velocities for every single atom. So in this way, if you have to restart a run that, for example, crashed, you can restart exactly with the same configurations without having to invent anything and knowing actually exactly the kinetic energy and thus the temperature of the system. So another question could be, why do I use Q and Q dot, where actually Q dot is a shorthand to say the time derivative of the position, simply a short way. It's because in Newtonian mechanics all the formulas and all the equations we get are dependent on the kind of coordinate system we use. They work very well in Cartesian coordinates, but every time you change coordinate system you have to recalculate your equations, or at least to change them. For example, kinetic energy in Cartesian coordinates is 1/2 mass and then the square of the velocity. But if you try to do it in, for example, spherical coordinates, this equation won't be the kinetic energy anymore. In fact, it would pass to some kind of expression where you have 1/2 a function of coordinates, so radius and the two angles, and then something that may remember this. So the time derivative squared of the radius plus the time derivative squared of theta plus the time derivative squared of phi. So this isn't the same thing anymore. Now, more on in the future, you might see that even with some other things that aren't Cartesian coordinates, I will use m, but it won't be the mass in these cases. So if in the future you see that I shortcut it, it's simply a short way to say actually that it's some unknown function. But let's say the Lagrangian formalism is actually coordinate kind independent. So it will work with Cartesian coordinates, spherical coordinates, whatever kind of coordinates you decide to use. And that's why you use q and q dot. And q is our called generalized coordinates or generalized positions, actually, and q dot generalized velocities. Actually, to say that there can be any kind of coordinate system. So once that we impose that the action must be a minimum, after some math that I will skip, we arrive to what's called the Lagrange equation. So the time derivative of the derivative with respect to the generalized velocities of the Lagrangian minus the derivative with respect to the generalized positions of the Lagrangian must be 0. So this is the Lagrange equation. As you can see by the eyes, it's actually a system of equations. These are second order differential equations, and they are as many as the degrees of freedom of the system are. So if we have s degrees of freedom, they will be s. Usually in a system of n particles, the degrees of freedom are 3 times n. So 3 times n. It is because each particle can of course move in each of the independent direction in space. It doesn't always have to be like that. For example, if you have a motion restrained on a certain space, so for example on a surface, then we would have 2n degrees of freedom. So of course it depends on the problem. That's a general situation, for example in molecular dynamics, where things can move quite freely. Once we have a Lagrangian of the system, by resolving this system of equations, we can get the equations of motion of our system. So, what is the Lagrangian? Now, we haven't talked about it yet. It's really simple. The Lagrangian is the kinetic energy of the system minus the potential energy of the system. So, each time an object moves in the classical world, it will minimize the kinetic energy minus the potential energy, and it will choose only that path between the many it could do. So, for example, from A to B, many paths could be chosen, but only the one that minimizes the Lagrangian will be the one that actually happens. At this point, some interesting characteristics of the Lagrangian. There are actually two. The first one, the Lagrangian is additive. So if I have two non-interacting bodies or particles inside my system, I can sum the Lagrangian of body A and of body B in order to get the total Lagrangian. Of course, this is true if the interaction is absolutely zero. It is an approximation if the interaction is negligible. But quite often the interaction is negligible, so you can simply sum the Lagrangians of the various particles. Another interesting thing is that if I have two Lagrangians that do only differ by the total time derivative of a function that depends only on positions and on time, they will create the same equations of motion. So once I solve one of them, I will have solved the equations of motion for every system with Lagrangian that differs only by this absolute time derivative. So writing it, if we have L and L first that is equal to L plus a total time derivative of a function that depends only on positions and on time, they will get the same equations of motion, so they will be equivalent. So for the last thing of this video, you might ask yourself, okay, but does actually this Lagrangian formalism really represent Newtonian mechanics? So if I use Cartesian coordinates, do I get Newton's equation? Spoiler alert, yes, but we're going to check it. So we're working in one dimension to make things faster. In one dimension, kinetic energy will be 1/2 mass x dot square, where x dot is the velocity along x, the one dimension we are using. And the potential energy will be simply some kind of function of x. Of course, where x is actually a vector, but I will probably forget about the vector notation. So the Lagrangian will be 1/2 mx dot square minus u of x. At this point, we are going to insert it inside the Lagrange equation. I got a little bit short in space, but so I have put my Lagrangian inside the Lagrange equation. So this derivative is according to x dot. So ux doesn't the potential energy doesn't depend on the velocities. So this derivative will be for sure 0. This derivative is according to the position x, and as the kinetic energy doesn't depend on positions, this will be for sure 0. On the other hand, the derivative according to velocity of 1/2 mx dot square is mx dot. Then the time derivative of mx dot is mx double dot. Here is simply minus and minus is plus, and then simply the derivative according to position of our potential energy must be 0. But by putting this by the other side of the equal, what we get is mx dot double dot is equal to minus the derivative in space of potential energy. But you might notice that this is m times acceleration, and this is how we define force. So what we got is again F equal m times a, and F equal minus the derivative along of the positions of the potential energy. So yes, it represents Newtonian mechanics.